Welcome back to High Performance Computing. Today we have lecture 1, the second part. In the first part of the lecture, we basically started the course now really with a focus on high performance computing. We introduced before in the prologue some of the concepts, but really on a 10,000 feet perspective. And now in this lecture, from the first part, we already dived a little bit deeper. We understood a little bit about the basically multi-core concepts, that we have several nodes that we interconnect. And this interconnect is one of the differentiating factor why we call a system a HPC system, which might be not necessarily a big, bold supercomputer that you have seen in the top 500 in the first part, but still captures the essence how we can basically promote parallel computing in a very efficient way so that we have lots of message exchanges between different nodes, what we call then distributed memory, which is an important architecture term in HPC. And of course, we want not to lose necessarily the effect of shared memory. So also this is possible, which is actually then often combined, as we learned in the first part, where you have essentially shared memory within a node where everyone can access a memory space, a shared address space. And then we have distributed memory, which is actually across the nodes. So these are important terminologies, important concepts, and many of this, what you have heard in the first part, we will look again into when we have lecture 2 on MPI, for instance, or lecture 5 on OpenMP for shared memory. So this is just also, let's say, a warm-up to get you into some of the terminologies and important aspects of HPC. So the first part was also a lot about hardware in a way, and also, despite the fact it's basically also a programming model, still constitutes how we create these systems. We will extend this a little bit with the many core aspects now in the second part, but also will have a much more interesting view on the whole HPC software ecosystem of technologies, which we basically will now have in part 2. We start essentially by an overview. What software environments are important? And you see here, this is on different levels. Needless to say, as you have seen already in our last practical lecture, Unix and an operating system is, of course, still available. So sometimes it's a more or less reduced Linux derivative or a reduced Unix system, not necessarily the full-blown one that you maybe have on your laptop, but still, of course, is taking care of the processes of the whole elements. That is basically something which is every time there. Then another key consideration, that's why our next practical lecture 1.1 will be all about it, is the scheduling concept. This is a bit harder to understand. It usually is the point that this supercomputer or a H machine is a concurrent access machine. So basically many users at the same time, I repeat, many users at the same time operate on the supercomputer. Needless to say, it's not a resource that you have just on your own. Basically, you share that cluster or this HPC resource with many other users, and there must be a concept to enable then that all the work you do is not hindering others, but also, enabling you to do the work of the size you want. This is a concept called scheduling, and as I said, we have a whole practical lecture, basically the next time on it, where we basically see Slurm on Newton and also again on our deep clusters. It's also basically one of the wordings where you basically have heard maybe before or will hear that HPC systems are often operated as batch systems or batch queue-based system, because essentially that means that we put the work that we want to do on a supercomputer somewhere actually in a queue, and then it will be worked on at a specific time when there's space enough, and basically in a way that it not hinders other users. Hence, this multi-user environment is very important. This refers also into the next point. When you have multi-user environments, you want to monitor the system, not only if there are broken parts of the large HPC machine. You can imagine when they have a multi-node rack system, really lots of nodes, lots of racks. And in the next couple of lectures, you will see what a lot of nodes really mean. For instance, in Summit or so, in the HPC system by the US, which is pretty much a supercomputer these days. You have many of these different users. They all have their different jobs or their activities on this. And of course, we have also the problem the hardware fails sometime. So we need some monitoring of the whole system, not only about the load, which is given to us in a sense by the scheduling system, but also, of course, about the system health. So are cores broken, overheated? Is there a problem with the storage? Is the parallel file system not anymore basically reachable or is down? So there are different systems where we'll basically also, again, we'll look into also in the next lecture already with LLView, Ganglia, and so on, Inca. The next area then is basically a little bit different, you would say. We move a little bit from the typical operations of HPC through something we call tuning of HPC applications, but there are a wide variety of HPC system software stacks available that help you to measure the performance, analyze the performance, and then also recommend improvements. Like for instance, Scalaska, when we have certain patterns where basically we can already observe that the program was, of course, done in parallel maybe, but not efficient enough. So there are problems and errors or maybe improvements. That's why we call it tuning. There are systems like Scalaska, Vampires, Scorpy, many of them available in this area. Obviously, it matters to us. That's why we want to have HPC. That's why we use HPC resources in the first place. So this performance analysis is usually a very big part in this HPC system software. Also, for another reason, as you can imagine, the bigger the HPC machine is, the more money it costs. Especially the interconnects of these nodes are very costly. So you want to avoid to use these resources basically inefficiently, or to have even maybe here and there parts idle waiting for other processors, which is a topic in MPI we will come to when we talk about barriers and idle time and load balancing in one of the next lectures. Then the more HPC becomes stable, the more it becomes basically more mainstream, you could say, more and more people actually use HPC these days than 10 years or 20 years ago, the more we see the uptake of advanced middleware that actually simplifies the access to HPC. There's something called Rescale, a system which has lots of applications already basically ready to run and is possible to deploy on HPC systems. And we will also look later into this, how we do this in Iceland, for instance. But there's been other middleware in the past, for instance, Unicore, or basically also the RACE framework that we have in development in basically the Center of Excellence RACE here in Iceland, together with Germany and other players. This also works on the simplifying access, particularly for AI. So interesting to see, although HPC is quite a hardware-oriented topic, it is equally also important to consider always a system software with it. Otherwise, you have a system which you basically cannot control and cannot basically even understand what it's doing, especially if multiple users at the same time. When you think about scheduling, what we said we want to explore in the next lecture, there's an interesting, more recent approach to also enable supercomputers with interactive access, the so-called interactive supercomputing approach. Now, this is in really contrast to the batch system I just mentioned. So you will be put in a queue, you will wait maybe a day, and your job will work tomorrow. And here we see interactive supercomputing approach, and using this Jupyter Hub technology, basically you are able to use a Jupyter notebook, an interesting environment that enables you really working basically instantly on a cluster, on a HPC machine, and leveraging the environment. We see that this is actually quite a bit more complicated than just providing the SSH key in a sense for the system. But for you as a user, it's a very nice access. So basically just have your username, password again, opening Jupyter on these machines, and you're in. From the backend perspective, lots of things happening with identity management, with Unity and Unicore X that you see here, in order to enable you with all the different steps to, in the end, get also access to this HPC machine, basically without scheduling. But this is not correctly true. So scheduling will still work in the behind the scenes. But you basically, as a user, don't have to put your job in the queue. You basically automatically with Jupyter have a job, an interactive job, so to speak. You can work with HPC machine. Also, this is something what we will explore in assignments. So if you completely not understand directly what I mean with this, This is something where, of course, you will learn that a bit more in the course. Now, the architectures, again, also thinking about what that means now more from the software perspective. Usually these machines are extremely complex. They have different multi-cores, many cores, multi-threading capabilities, all different cache levels, the network topology, and actually how you play and basically use it. Network topologies is also a very important factor as the real physical interconnect, which would provide high performance. The interesting different architecture impacts in the designs of all the vendors. So, which makes it then to understand that HPC is really in one way the Formula One of computing, right? What you want to have is really having something which is or enables you to be on the forefront of computing, so that you basically can have jobs with cutting edge performance and what has been done not before. Hence, this also provides us with challenges. So here and there, the hardware is not ready enough or stable enough, for instance. We have certain changes, for instance, the IBM Blue Gene supercomputing machines that you see here in the back. It's a very good example. We had a Blue Gene L, a Blue Gene P, a Blue Gene Q in Jülich Supercomputing Center during my time there, but suddenly IBM decided to drop this line. So suddenly all the architecture concepts where your teams have been basically performing support, know the architecture very well, suddenly had to really stop in this direction and have to basically get acquainted with complete new vendors, like from Atos Systems or more recently also again from Cray. So this is something which is in HPC along the way, that the architecture advanced so quickly that sometimes it becomes obsolete or slow. One example will be also the many cores. When you think we had Keplers in the past, suddenly Voltas, then Ampere, so A100s, basically then before V100s, K80s. So this is a technology, this many cores, we will look into it, which is also something which evolved very, very fast and always are new capabilities. Let's say, for instance, tensor cores that helps us also in deep learning. How you build this together, here's an example which is a little bit older from a Blue Gene P and Blue Gene Q, but it doesn't actually change anything. It's just a very nice illustration from IBM I borrow here. So that's not from myself, that's really from IBM. But it shows you nicely that one chip is, of course, as I described in the first part of the course, still the main part of it. Then you would put them on a compute card in order to put them very dense in so-called node cards. And these node cards are then ingested basically in a rack, which is also very dense, in order to compile then this big system that you have here, which then maybe so it's here is 72 racks, or in this Blue Gene Q example here, much more. And of course, the technology behind it changes, right? Especially from these two different lines here, P and Q, there were several years. And sometimes the modality, how many put you basically on the modules and on the compute cards change, but the overall idea of using the node cards, drawers, midplanes, and constituting racks is basically a key concept again, where this is a beautiful example how that works in this HPC. So you don't not only put essentially now the laptops, put an Ethernet cable to it and connect another laptop and another server. So that's absolutely not what it's done in HPC. It's really an integrated set of very densely connected computing power. And also here again, the internet connect matters, but also the cooling that we basically will explore in one of the subsequent lectures needs to be also very well done, as well as, of course, basically you see here, they always stay in halls with a second floor for the network interconnectivity, but also in halls which are then provided by argon gas or some other element, because you don't want to have water for putting out a fire. So hence there's a whole ecosystem around it from the hardware, and as we've seen before, also for the system software, which then makes it a really, let's say, complex technology really, than just essentially our little laptop that we have on our desktop here. So looking a little bit more when I talked about topologies, terminologies around this is a little bit something you should understand. Obviously, we have a physical network interconnection. So these racks and nodes are really connected, not only with each other, but also, of course, to specific storage entities, where you basically have InfiniBand, for instance, as a very powerful interconnect. So this is different than Ethernet in performance by far. And the way how you then use this network can be different. So you see here an example of a torus network. This is how you then can leverage this interconnects, but with different, let's say, network topology that you can steer within your application. And they have all the different, let's say, ideas how to use it. Today, we have also Dragonfly and other interconnects and topologies, really, which makes it also, again, on the network alone already a very complex matter. What to use, what not to use. And of course, sometimes we have even I/O nodes, which are then different from typical compute nodes, because in one respect, you want to save your results from the HPC system computation, but also maybe load some initial situation into your application. So this means we have also a lot of I/O traffic, which goes into the network performance and is also something to be considered. Hence, this is something we will look also into when we talk about communicators a little bit in the next lecture, starting with MPI and so on. Obviously here, that is a quite deep topic. Then I think, but we should mention one of the continuous developments here. And of course, for many of you know the GPU probably from the gaming industry long before HPC basically directly made use of it. But basically, this is something of what we call this new emergent system parts. And this was not only GPUs for HPC, there were also field programmable gate arrays, FPGAs, that have actually a specific integrated circuit, which is a little bit harder to program, but enables, of course, quite nice speed basically in with wired interconnects and so forth. Then there was a cell processor as well. So basically, you see that always new architectures of processors. Today, we have actually a TPU, a TensorFlow or Tensor Processing Unit. We have even a graph-oriented design of processor units today, which I will also down the road here in this course will show you. So this is an interesting aspect that basically HPC always deals with new hardware. And at that point in time, perhaps when GPUs were just on the horizon, it was still very important to think about FPGAs as well. But they really won the race, so to speak, in the moment of something we call this many core, which basically solved a little bit the problem that we had basically in the CPU. I talked about the limits of the clock speed, the overheating of CPUs. So there's a certain limit that you cannot stick more cores on a chip, will be too hot. And this is what the GPU in a way really mastered with the many core. And you see also NVIDIA CUDA, this was certainly the first ones, but now we have also AMD and other manufacturers that going into the same direction. And they, not only because of this aspect of the limits of the CPU, with the many core GPU, you will see also you can speed up computation, which is very brilliant for artificial intelligence with deep learning and tensor computations like matrix multiplications of certain kinds. But all of this will come down the road in the deep learning lecture, so that's not overdoing it here. But I think it's important to understand that the GPU not just popped up and everybody was happily using it. There were also other concepts around and are still around that basically in the future perhaps will play a bigger role, like neuromorphic computing, and even now we think about quantum computing. Coming now a bit more what a many core really is. I talked to you about a lot, but when you compare it to the CPU architecture that we had before in part one, you can see that the GPU has really very many of these processors, but this is important now. They are not at the, let's say, high clock speed rate. These are moderate performance chips, but the benefit that you have here, they will not be getting too hot. So you can have just a lot of them on the chip. Hence, it basically puts on a bit of a brake and say, let's basically have not every processor very high clock speed, high single thread performance. Let's lower that, but have very many of it. And a little bit it alludes to this HTC aspect of high throughput computing, have many, and you think just about the throughput. And for some problems, it's really a good idea to do so, especially of those that you can be, again, nicely parallelized for a certain part. The downside of the GPUs that we have today, and many people work on this extensively to get maybe rid of this tomorrow. We have, let's say, NVIDIA GPUs, for instance, that unfortunately right now still have to go via the main memory in order to fill the device memory. From there, you can do some exchanges to the other GPUs and so on, but somehow this bottleneck of going to the CPU main memory over to the device memory is something which limits certain applications. That's why many hardware vendors right now, when they think about GPU design, also think about of combining a CPU with a GPU to have a standalone system. But this is, let's say, by far still, while we have a huge collection of NVIDIA GPUs all around in Europe and around the world, still probably one of the major bottlenecks. Hence, a GPU, we will have a complete lecture about it. And we will talk about also new accelerators, which will be coming not from NVIDIA, just to show you that there's more and more heterogeneity there. But this lecture will come down the road in lecture 6, so I don't spend much more time on it. Of course, they came with lots of benefits, as I was alluding to already, with vector matrix multiplications. Just to show you a little bit here in this color coding, I think this is an important part of it. You see, when there's a problem that can be nicely parallelized, like for instance here the matrix vector multiplication, you see this with the color coding, where no interaction is actually taking place in the matrix to the side, right? Column by column, you can actually parallelize this beautifully, and it just operates with one part of the other vector. Hence, as we had in the HTC-oriented idea, although we do HPC with GPUs, this is a bit nicely independent parallel. And this was one of the benefits now that you can map beautifully to this GPU in this different, let's say, many cores, while each operation is just here, for instance, a simple, multiplication, not a differential equation and lots of iterations. So here we have a very straightforward computing process, which can be executed quickly. And basically you don't have any interaction with other parts of the matrix. So you can crunch down the matrix in small and basically leverage then the huge amount of processors. And with huge, I mean really hundreds and thousand cores these days, which then can be actually operated on a lot of more threads. But yeah, lecture 6 will capture this in more detail as a slide, also with lots of updates, obviously, to the different vendors that are coming with all their unique selling propositions. One idea why now, also this GPUs got quite an uptake was a new field in the artificial intelligence area. It's not particularly new, to be honest. So deep learning has been around for decades, but now we have the computing means to do so through this many core technology. And this, of course, raised a new, let's say, summer in AI, as the people will call. There was a winter of AI since the neural networks were the last developed, and you could go deeper in the past. And this was basically something where no major improvements were. But now with deep learning algorithms, we will have a whole lecture 7 about it. They're really groundbreaking news in terms of image recognitions, of here's a character recognition. And one of the takeaways here really from this slide should be that deep learning also is not just computing deeper in a neural network, but also with very specific layers and very specific AI architecture types. So this is an important, will be part of lecture 7. I give you a sneak preview with a video here, how that works and why deep learning needs then also lots of processing power, will be part of lecture 7. I think you can see a little bit this lots of different connections between so-called layers, for instance, in the multi-layer perceptron, and all of this mesh-like oriented elements you have seen growing actually over the course of this video I showed you mean also more and more computation. Although these computations are relatively simple, you have very many of them, especially if you add, for instance, more neurons in each of these layers. And all these connections in one way or another mean computing. It's clear that this is not obvious to you. We will see how that materializes when we go to lecture 7, right? But take away the message that these, of course, then can leverage GPUs very well, and which basically also then now has created a new form, really, how we tackle certain AI problems like this character recognition here that you see is relatively a toy problem, but you have seen in the video, we ended here with this convolutional neural network, something you see here, where really the first part is something that would like to explore features and feature maps really of these characters in order to perform then a classification of if this digit is now an 8, a 9, or whatever. So the breakthrough in computing in one respect enabled us to really create new breakthroughs in artificial intelligence with deep learning architectures, and there are very many. And the second half of this course with the CFD special this year will really touch base on many of them, the gated recurrent units, long short-term memory for sequential data, so time series data and so on. We will have also element aspects of character recognition, computer vision aspects. So there are different architectures for different problems. And I think this is a key goal here, while deep learning is really then making, let's say, breakthroughs probably every week in different problems we had before, but now we can solve them with very interesting deep learning algorithms, where the limit is more or less only the computing power, and then perhaps also the computing power needed to steer all the hyperparameters. Hence, this is the next topic. How you use computing these days is not only to improving one network and train it, and basically then doing something called testing and validation and so on, things that we learn a little bit more in lecture 7. The other aspect, how you use HPC significantly, is really finding the right hyperparameters. And this is now a more or less already advanced concept. So in lecture 7, we will learn what a hyperparameter is. Here are some examples. So the optimizers you choose, activation functions you choose, the training epoch, the batch size, the learning rate, etc. These are all different parameters which you need basically to train a neural network. And you never know if that's really the best way to train it. So you end up training it a lot of times. Here are examples actually in one of our research field, remote sensing, where we use here basically convolutional neural networks to identify the land cover, right? That we obtain from satellite data via hyperspectral images. That's what you see here. Hyperspectral means you see with different spectral channels inside the Earth. That's why we basically have more or less a cube than just a picture from the satellite. And this is analyzing the spectral channels here for, let's say, a certain region is something where we have used this and where we continue to use this with different deep learning architectures. And with this, all these different architectures, all of them have in common that the hyperparameter search bears potential to improve the performance. So with HPC, we not only speed up the modeling of AI, with high performance computing, we also make the models better through hyperparameter optimization. And this will also be something we will learn basically in one of the lectures. So a little bit to summarize and to contrast it again in terms of AI versus big data versus deep learning versus HPC. Here's an interesting slide that I once showed in the German parliament. It was considered to be a very interesting slide. That's why I show it again, because it captures quite nicely the essence of bringing all these terms together on one slide. You would say, in a way, in HPC, we work with big data. When you do big data, then you essentially have the problem that many of the traditional AI systems you see here, random forest SVMs, and if you do it with basically non-parallel versions with scikit-learn or Weka, Octave, MATLAB, They all break in terms of memory capacity and also of computing capacity. So basically in the past, this was never a problem, but nowadays, if you have now essentially more and more data, we come to limits. And that is exactly the input what deep neural networks need. The more data you have, basically the more big data you see, these curves go really up. They particularly don't work very well for small data sets. So deep learning, all of these neural networks usually have a problem that they work not so good with small data sets. So there you better go maybe with random forest or SVMs. But if you, let's say, swim in data, then chances are basically you have a much better model performance or accuracy if you use small neural networks up to large deep learning networks like transformer models or GPT models for language as we know today. But if you do this step, and now you see basically the footprint of computing here, the training time as we call it, could be also hyperparameter optimization time, which in the end trains again with different parameters, again training time, but you need high performance computing for that. Not only for the training, but also basically then for this hyperparameter optimization, where high performance computing resources and cloud computing resources these days are really key. Otherwise, you would never end up with this large network that we have today, like for instance, this large network language models you probably have heard from. So you take the price and have the computing, but of course, luckily high performance computing resources are becoming also more broadly available. For instance, in the Euro HPC joint undertaking in the European sphere, there are different supercomputers available for researchers and engineers for free. All you have to do is basically to provide a proposal, especially if it's in the academic sector. There's a little bit for industry as well. I will also have a little bit more on this in the subsequent lectures. For industry, there are some basically initial parts where you can use the systems at least for free, like an SME, for instance. When you do this, cloud computing is, of course, something which is also used in this context. I just wanted to say here a couple of examples with Apache Spark. If you heard about this, we would rather see this more in the cloud computing and clouds like AWS or MS Azure or basically Google Cloud Proc. And I talk about this much more in the complementary cloud computing course. So we don't have much attention here on Spark, but people have also ported Spark partly on HPC resources. So it's basically possible, but it doesn't leverage the interconnection so well. So that's why basically it's not really common to have a Spark cluster on HPC yet. Now, some relationships when I talk big data, what that means in high performance computing. Here's a very good example that I got from my colleagues, basically from San Diego. You see here, just to basically have a kind of earthquake simulated in a TerraShake domain. We have here 1.1 terabyte for surface data and then 43 terabytes for the volume data, because we also want to look into the Earth, obviously. But you see, when we increase this with 1 trillion mesh points, so much more accurate, right? The domain also bigger. Then, of course, we are increasing the data significantly. Suddenly, we have 1.2 petabytes or 4.9 petabytes volume data. Of course, this means better prediction accuracy. And of course, this means also bigger data. Then the memory gap is quite dominant today as well. I said to you, the main memory is still very fast. Of course, the caches is the fastest beside the register, of course, but then the capacity is limited. So we have to go to disks or even tape archives for large data sets. These, on the other hand, need quite some time to actually be, going first to disk and then from this tape archives back via the disk to main memory. Hence, all of this is a little bit what we call right now the DRAM gap, more or less, basically that you have where it's a large discrepancy between the main memory and the cache bandwidth that we have here. And also, more broadly speaking, the whole process of storage limits us what we can do in compute. And I will talk also in several lectures about it. However, big data drives then, of course, this HPC architecture designs, more modularity. You have seen the data analytics module that we have, for instance, in one of these systems like Deep, which is much more oriented towards working with large amount of memory. For instance, the Spark cluster associated directly inside this HPC system as one example. Here people have done different tiers where each tier has different responsibilities in terms of memory, disk space, and so on. We talk about this about hierarchical storage management that will also come every now and then in the course. Just that you basically understand that today, in a way, you could say that CPU speed really has surpassed our storage and I/O capabilities of existing HPC resources. Computing is cheap these days, but we need better concepts for storage, for actually hierarchical storage management, and scalable I/O, which actually here and there are real limits. And we do this by exploring the modular supercomputing example and the architectures around it. I was already basically presenting this just to capture again the idea of this data analytics module, for instance, when you have this high memory intensive applications, but of course also the scalable storage service module with a parallel file system, a concept I will also allude to when we have advanced concept of MPI that we write basically in parallel with many processes into one file to make it scalable. So hence lots of approaches. And I also would like to invite you to look at HPC more broadly, especially when you think about what we do here in Iceland. Obviously, I cannot teach everything, but many of our colleagues in different parts of the university have also interesting lectures referring to computational chemistry. We have here a lab in our EuroHPC Competence Center in Iceland about HPC, funded by the EuroHPC joint undertaking. And this computational chemistry has experts like Hannes, who really also basically has courses on how you leverage chemistry. Then with HPC fluid dynamics, Austis has concept for fluid dynamics that we leverage with HPC. And you can go on and go on there. Natural language processing parts, AI parts from Hafstein that leverage HPC. So this is a way where you can, on one website, see essentially where are the players in Iceland on HPC and how we basically build a community where you can be part of. We're doing several workshops in this course. You will see soon in February, we have the next one, where you will be also invited in to be part of our community. And also when you, of course, graduate, you're still welcome to join maybe one of the simulation data labs, or even if it's just presenting your insights from the company at the EHPC workshops. That has some history. The EuroHPC JU, especially before there was a concept called PRAISE. Also in the US, there was a concept called Extreme Engineering and Discovery Environment, EXCEED, which was essentially the US HPC infrastructure. Both of them actually have stopped these days. So it's more or less a news that the EuroHPC JU is at least taking now basically over many of the activities from PRAISE in different projects and different entities at the main office. And Iceland is part of the EuroHPC joint undertaking, which enables us also to get time on this HPC resources. And of course, this is the same basically for grids and grid computing. If you heard that in the past, more or less, we talked there also about basically clouds today. Also here at CERN, I'm talking about CERN in my lecture, quite interesting. I'm right now recording this here in CERN. So basically you see here that also the grid computing approaches with some publications of the past, basically alluding now to many of the parts we have in cloud computing and the European Grid Initiative and so on. All of them share in common, they have a very diverse user community like HPC. And with this, basically, I talk also more about the clouds and so on as a sneak preview for the cloud course, if you're interested, and would just close here today with the emerging quantum computing field. This is something where we, I think now would be able to do a cool course in which we maybe do soon in the future, also maybe joining up with cybersecurity a little bit, things like quantum cryptography and so on. We use it already for certain smaller problems in remote sensing. Again, land cover, classification of satellite images and using, for instance, SVM, a specific format on it. So there are lots of different concepts in quantum computing. We use a D-Wave system. And if you want to learn a bit more about quantum computing already, you can go to my UT Messan talk on YouTube. UT Messan is one of the IT conferences here in Iceland, where I just once also gave in 2020 before the pandemic, basically also an update on quantum computing. In one respect, you would say, instead of having a 0 and 1, what we know from computing, or hopefully all of you, which you have either or, you would say what we do in quantum is we have 0 and 1 at the same time. Superposition, entanglement, bringing more of them together. These will be all then topics of lecture 15, where we basically have already concrete results using a real quantum computer existing also at the Uli Supercomputing Center. And this is really all I wanted to basically leave here on the table. Obviously, there's a video that summarizes a bit what computing in terms of HPC means, why supercomputing is needed. You see here Earth climate is probably one of the most important one, because if the Earth climate is not anymore good for us, then it's hard for us to live. So, but there are many different applications from medical up to others. So I encourage you to look this video in your part, basically in your homework. And I would say we see us again in practical lecture 1.1, where we then will go a little bit more deeper into scheduling. So see you then.